Thank you. I was going to say it's a great pleasure to be here. It's a great pleasure to speak at this meeting. I'm sorry I'm not there. There's this conflict with MSRI program, which ended up being at the same time, which is where I'm now. Sorry. Let's see. It's a great pleasure to say wish happy birthday to Kobe and Sergey. These are two people I've known for over 30 years. I think I first met Kobe here at MSRI in 1989, and Sergey when he took incriminating pictures of me in 1991. These are two people who I've greatly enjoyed talking mathematics. Also, both of them have spent, Sergey spent a year in Chicago and Kobe spent most of a semester. And these are two people I've greatly enjoyed spending time with and talking mathematics. And I'm sorry I'm not there to celebrate their occasion today. The work I'm going to talk about today is joint work with Jim Freitag, Remi, Jaoui, and Ronnie Nagloo. And it's in the model theory of differential fields. So we're going to work throughout in K some ambient, large, saturated, differentially closed field, and C will denote the field of constants. So a definable set is strongly minimal. Recall if every definable subset of X is either finite or cofinite. And usually I'd have to go to a bigger model, but I'm assuming I'm in some kind of saturated model, so this is fine. The Shalom philosophy is that to understand finite rank sets in any kind of structure, what you do is you first understand the strongly minimal sets, and then you sort of understand the algebraic relations between the strongly minimal sets. And this will allow you to build up an analysis of finite rank sets. So the project is really to try and understand strongly minimal set. This is a big project. It's to try and understand strongly minimal sets in differentially closed fields and trying to understand the algebraic relations between them. So just a brief review of the sort of the fundamentals here. When we're trying to understand a strongly minimal set, we try to understand how the algebraic closure on that set works. Algebraic closure, I usually mean this in the model theoretic sense of things that are in a finite set definable over the structure. Here, that has a very concrete meaning that the model theoretic algebraic closure, which I'll denote CLA, is just the algebraic closure of the differential field generated by A. So you close A under derivatives and field operations and solve polynomials over that, and that'll give you the model theoretic algebraic closure. Okay, so let X be strongly minimal. Then we have the usual sort of Zilbert classification. In some sense, the simplest, but as we'll see, in some sense not, are the strongly minimal sets, the geometrically trivial ones. This is one where the algebraic closure relation is basically unary. The closure of A is just the union of everything. Oh, sorry, this is a typo. The closure of A should be the union over big A of the closure of singleton little a. So anything that's in the closure of A is in the closure of a single element of A. So a classical example of this would be, say, just the integers with successor. In differential fields, we often use it in the following form. Suppose I have n elements in the strongly minimal set, and I take these, what I call the bars of these elements, which is just the element and all their derivatives. Then if you have a dependence in the sense of forking, or if the field generated by, if you take the fields generated by the y1 bar up to yn bar, and these aren't algebraically disjoint, then you can actually find two of them. So the dependence comes between I and j. So we don't have complicated dependences that depend on, I can't have yk depending on yi and yj, but not on either one of them separately. Then we have the locally modular things, and the trivial things are examples of locally modular, but the locally modular things, whenever C is in the closure of A together with a set A together with a singleton B and not in the closure of A, then B is in the closure of A and C. So this is the example here to think of is dependence in a vector space, or in general in any kind of group. You'll always get this kind of property if you just look at closure in the group relation. And then the third is sort of the otherwise. If it's not in one of these bins, it's in the locally modular bin. So the three things we want to really look, the non-locally modular bin, the three things we want to look at are the geometrically trivial, the locally modular non-trivial, and the non-locally modular.
I mean, the second thing is just the fact that it's of rank 1.
Pardon?
Just the normal exchange principle.
Yeah.
Your second item is just the exchange principle. That's always true. That has nothing to do with local modularity.
Oh, sorry. Sorry. Right.
That's okay.
I was in a single set of small a there.
Yeah, sorry. What I meant to write here is that there's an A. There's a little a in the closure of big A, such that B is in the closure of A together with C. Sorry, I can't correct this on that time. Yeah, sorry. I did this a little too quickly. Sorry. Yeah, you're right, Zoe. Thank you, Zoe. So this should say that if C is in the closure of A and B, big A and B, little b, then there's actually a little a in the closure of A, such that C is in the closure of little a and B. And again, this is what happens in a group. Okay, sorry about that. I hope the rest of the slides are a little more careful. Okay, so the first thing that's interesting is that in differentially closed fields, all three of these things occur in sort of a fairly natural way. For our purposes, it's going to be, we need to talk about when two strongly minimal sets are essentially the same or essentially different. And that's going to be the model theoretic notion of non-orthogonality. And for strongly minimal sets, being non-orthogonal, which means being the same or being intimately related, just means that there's a generically finite to finite relationship definable between X and Y. So that a generic element of X is interalgebraic with a generic element of Y and vice versa. Okay. So here are some of the early examples. So the simplest example is the field of constants. This is a strongly minimal set. And indeed, any definable subset of C to the n is already definable in the field structure on C. So the constants really, even though we're embedding them with all this extra differential structure around them, the things I can define on the constants are the things I could define just in the field language alone. Okay, so this is a non-locally modular example. Okay, it's easy to see that if I have an equation of order 1, so it involves first derivatives but no higher derivatives, and I can't factor it, then it's going to be strongly minimal. And interesting examples of this were found, in the 70s by Rosenlake, Kolchin, and Shalom independently. And they gave examples that are geometrically trivial. So a simple example is this equation: x prime is x cubed minus x squared. So if you look at the solution set to this, you've got 0 and 1 are solutions, but then any other solution, the rest of the solutions are a complete set of total indiscernibles. So there's no structure on those whatsoever. And that's sort of often the case in the trivial ones. Not always, but often. The other early example, which we'll be coming back to a lot today, is this example due to Poizat. So I'm going to write this in the form where it's strongly minimal. I take x double prime divided by x prime, and let's set that equal to 1 over x. So this is a second order equation. It is strongly minimal. And because it's order 2, it has to be orthogonal to the constants. So I think this result was from the early to mid 80s. The next big jump in the subject came with the work of Hrushevsky and Sokolovich in the early 90s. And there we found the first examples of non-trivial locally modular things. So these come from algebraic geometry. Let A be a simple abelian variety. So an abelian variety, the word abelian should be there, that is not isomorphic to one defined over the constants. So I've got this kind of algebraic group that simple means that there are no proper abelian subvarieties. So there are no infinite algebraic subgroups of A. And now, just using the model theory of omega stable groups, we know that there's going to be some kind of minimal infinite definable subgroups of A. And we let A sharp be one of these. So in this case, A sharp, you can give it a geometric interpretation. It's just the closure of the torsion points in the Colchin topology. Okay. And then what Hrušovský and Sokolovich proved is, first of all, these are strongly minimal and they're locally modular. Again, it's important that these are not, the varieties are not isomorphic to ones defined over the constants for this. Moreover, this is a complete classification in some sense, that any non-trivial locally modular strongly minimal set is non-orthogonal to one of the Manon kernels. So this is, in some sense, not only did we find new examples of these things, but we found all of them. Finally, we understand non-orthogonality here, at least up to algebraic geometry, in that two of these Manon kernels are non-orthogonal, so essentially the same, if and only if there's an isogeny between A and B. So this means an algebraic homomorphism that's finite to one and surjective. So this gives us a sort of complete understanding of the locally modular non-trivial case. Hrušovský and Sokolovich also give a complete understanding of the non-modular case. So the Zilber principle, you expect in case of a non-locally modular strongly minimal set in some kind of natural setting to be a field, and that's exactly what happens here. That if X is strongly minimal and not locally modular, it's non-orthogonal to the constants. So the constants was an example of something like this, but what this theorem tells us is it's the only example. So this is the only non-locally modular strongly minimal set. And this was originally proved using the Hrušovský-Zilber-Zariski geometry machinery, but later given a more conceptual proof by Pillay and Ziegler that avoids Zariski geometries completely. So with these two results, we understand the non-locally modular and we understand the locally modular non-trivial. So the question is, what can we say in general, or what do we know about the non-trivial? Sorry, this should say trivial. What about this trivial strongly minimal sets? Okay. So we gave you Poizat's example before, which we'll come back to, and their transcendence degree 1 example. So one of the theorems here that gives a complete classification is, well, and this is actually, I think I credit this to Rosenleek, but most of the tools are to Rosenleek, although I think this was proved by Tracy McGrail, that suppose I have just an equation x prime equals f of x, where f is a rational function over the constants. Then Rosenleek characterized exactly when this is trivial, and it's based on essentially on looking at the partial fraction decomposition of 1 over f. But it's a fairly simple. The proof isn't so simple, but the classification is a fairly simple classification using the nature of the function f. Some other transcendence degree 1 examples, sort of in the late 90s, were found by Hrušovský and Itai, who were looking at strongly minimal subsets of algebraic curves defined over the constants, assuming they had high enough genus. Moving on to this century, there's the work of Nagloo and Pillay, who looked at generic Pan-Levé equations and show that they were strongly minimal and trivial. So I give here the example of Painlevé 2, where t is something which has derivative 1, and alpha is a transcendental constant. Then they showed that these examples were strongly minimal, and examined the algebraic relations between various equations of this, and have some results about what happens when alpha is not transcendental as well. But these were and I just wrote down Painlevé 2, but they did this for all of these equations. And I should say that for Painlevé 1, this is actually an old result of Colchin from in a letter to Carol Wood. Again, by a fairly complicated calculation. Another example from 7 or 8 years ago is due to Freitag and Scanlon, who looked at the differential equation satisfied by the J function and showed this is strongly minimal. And this is the first example that had that was an example of a non-Aleph zero categorical trivial strongly minimal set. There was a question raised by Lascar and Poizat whether all the trivial ones would be Aleph zero categorical. And this is the first example that shows they're not. And this has been greatly extended in recent work by Casal, Freitag, and Nagloo, and then later the three of them with Blasquez-Sans. And they work on differential equations satisfied by uniformizing functions of Fuchsian groups. So what's interesting is that basically it's hard to show any particular differential equation is strongly minimal for the most part. I mean, you need just going back, the Rosenlich example is very specific using partial fractions, but also the proof is actually non-trivial. It uses a lot of things about there's some very algebraic things about Kähler differentials that come into this. The Hershkovsky-Itai results were quite special and used a fair bit about differential forms on curves of positive genus. The Nagloo-Pillay results used a lot of the differential algebra developed by of Painlevé equations developed by the Japanese school. So it's been fairly hard to show any particular equation is strongly minimal, but there's a sense in which there's some results that are quite recent that are sort of arguing to the point that most equations are. So one I'll give you by Remi Jaoui. I want to look at a vector field in the plane. So a system of two equations where P and Q are polynomials, where the degree of at least one of them is 3. And these are polynomials over the constants with so generic constant coefficients, so algebraically independent coefficients. Then these will always give rise to a strongly minimal set. So even though it's somehow hard to prove one thing is strongly minimal, here's a whole family of things where, unless you're in some special situations, they're going to be strongly minimal. Another result of this form is a recent result of Delibes and Freitag. So take a generic differential polynomial of order n greater than 1 that has degree at least 2n plus 4. Then this is going to be strongly minimal. Here, generic means with differentially independent coefficients. So there was a thought early on that somehow the order of the polynomial would tell the order of something would be a strong indication about what the Morley rank was. And this really says no, that when you look at families found in nature, that generically you're getting strong minimality, that there's very little extra differential algebraic structure on the definable sets. Okay, so that's the survey part. I really want to go on now and go back to Poizat's example and talk about the family of things we've been looking at. So Poizat, you start by looking at the differential algebraic variety. X is x prime is x double prime. And what Poizat proved was that there's only one differential algebraic, an infinite differential algebraic subvariety of this. And that's the one given by x prime is 0. So the constants. The constants is a subset of this. But it's the only infinite proper differential algebraic subvariety. So this is a situation very different from what you would expect in algebraic geometry, where once you have something that's sort of transcendence degree 2, you would expect it to have lots of transcendence degree 1 subvarieties. But here that's very wrong, that in this case, there's only one. So the corollary to this is if I get rid of this x prime equals 0 part by dividing out, and look at this equation, x double prime over x prime is 1 over x, it defines a trivial strongly minimal set. So why is it trivial? Well, this is a folklore result that anytime I take a strongly minimal set, if it's defined over the constants in order at least 2, it's going to be trivial. I mean, order 2 tells me it's that it has to be orthogonal to the constants, because it can't be interalgebraic with something of transcendence degree 1. And the fact that it's defined over the constants tells me that it can't be orthogonal. It has to be orthogonal to every Manin kernel. This is just, this takes a little bit of work using the machinery from Hrušovský-Sokolovich. But this gives an easy test for triviality in a lot of the examples we're going to be looking at. So if you look at things defined over the constants, as long as they're not transcendence degree 1, then you know it's orthogonal to the constants. Okay. So in our work, as we're looking at generalizations of this, namely, we're going to look at arbitrary rational functions over the constants and consider the differential equation, z double prime over z prime is f of z, and let f of z, v of f denote the solutions. And the theorem is that we can give an exact characterization of when these are strongly minimal. Namely, they're strongly minimal if and only if I can't integrate f in the rational functions. Okay, so I guess there are two interesting things about this theorem. One is I've given a somewhat interesting family where we can give a complete characterization of when the sets are strongly minimal. And again, these will all be trivial because they're order 2. The other interesting thing I think about this is, Poizat's proof is, while elementary, it's, if you look at my lecture notes on differential fields, this is 2 or 3 pages of painful calculations in polynomial rings, in differential polynomial rings, and it's really only applicable to this equation, z double prime over z prime is 1 over z. Rostovsky later generalized this. He found more equations where Poizat's method worked, but it was still a fairly a painful calculation. I'm not sure many people have read even my treatment of it. And what's interesting here is our proof is sort of very short and rather memorable, I think. So one direction of this is easy and was, in fact, I think noticed by Poizat. I mean, suppose I do have an antiderivative of f. Then if I look at the family of curves, z prime is g of z plus c, when I differentiate that, I get solutions to my original equation. So this tells me that not only do I have an infinite family, an infinite subset, I have this whole family parameterized by the constants of infinite subsets. Okay, so there's a whole family of order 1 differential algebraic subsets parameterized by the constants. And I've got a function from my set VF to the constants. Just take z to z prime minus g of z for every element of the set VF, and this will be a function onto the constants. We can say a little bit more about this case, and if I have time, I will at the end. But so these are the cases which are not strongly minimal. So we need to look at what happens in the case where I can't find an antiderivative of f. And let's just remember from Calc 2 what this means. So suppose I have a rational function. I can always do a partial fractions decomposition of it. So working over an algebraically closed field, the partial fraction decomposition is that f of z is the derivative of some rational function plus a number of these terms where if I were to integrate each of these, any one of these terms, I'd get a logarithm. And that tells me that, when I can find an antiderivative in the rational functions, well, it's only going to be if n is 0. So if I have none of these simple poles to f. So f can have poles, but the poles also all have high order. Okay, by a change of variables, which doesn't change the problem I'm looking at, I could assume that some alpha I is 0, so that I have a c over z term in this. And then I just want to look at the power series expansion of f. So writing f out, or as a Laurent series, the one thing I know is that if there's no antiderivative, there's going to be an antiderivative if and only if the a-1 term is 0. So since I'm looking at a case where I'm looking at a function f where there's no antiderivative, the residue has to be non-zero. Okay. So the a-1 term is 0. So that's the key factor we're going to use here. Okay, so suppose for contradiction that we're not in the strongly minimal case. That means we can find some kind of definable subset defined over perhaps some bigger field of parameters. And so that bigger field is going to be K. And what happens is then the solution Z and its derivative become algebraically dependent over K. So let's fix the case where I've gone to some bigger field K, and over K, I've got a solution to this differential equation that's transcendental over K, but Z and Z prime are algebraically dependent over K. Okay, and now we're going to look at this algebraically by passing to the Poizat series field over K. So we take the union of all the Laurent series fields in powers of Z to the 1 over n. And this is an algebraically closed field, so I could identify Z prime as some element U in this field. And now on this field, I'm going to look at a specific derivation on the field. So I'm going to define the derivation as follows, and think of this as two separate derivations. So for the first term, I just differentiate the coefficients. So this is the derivation I would get on the power series field, basically by making the derivative of Z 0 and extending the derivative of K. The second derivative I want to look at is the derivative where I make everything in K constant and the derivative of Z1, and that would be the second sum. So these are sort of standard derivations on power series, and I can find a new derivation by taking a linear combination over the field. So taking the sum of this first derivation and U times the second derivation will give me a new derivation on D. The important properties of this derivation is if I take an element of K, well, the second term will vanish. And in the first term, I'll just get the derivative of that element of K. So this derivation extends the derivation of K. And if I want to look at what the derivative of Z is, when I take the derivative of Z, well, this term will vanish, the first term vanishes, and the second term I'm just left with U, which is what I'm identifying Z prime with. So this extends the natural derivation on K of Z, Z prime, and then there's only one way to extend it to the algebraic closure, so that has to be exactly the way the Poizat series extended to the algebraic closure. Okay, so I've got this natural derivation here. Now let's, Z prime I'm thinking of as U, so that's some series in the Poizat series. And I'm going to write it out. Let's say it has value R. So I can write it out as a sum AI Z to the R plus I over N for 0 to infinity. And now I want to take the the second derivative of z, which is just the derivative of u, and I use my derivative rule on this series, and I get this expression. Now, looking at this expression, the important thing to notice is that this term, the valuation can only go up when I do this. I mean, some of these AIs may have derivative 0, in which case the leading term may get higher here. So the value of this term is going to be at least r. It might be higher. Okay. So since the value of this term is at least r, now what I want to do is I want to divide by u. So f of z is z double prime over z prime, which is du over u. When I divide this first term by u, I'm dividing something which has value greater than or equal to r by something that has value r. So I'm going to get something, a value greater than or equal to 0. And then I'm left with this second term. But this is now a Poisat series expression for f. And I want to look and see what about the coefficient of z to the minus 1. Well, in the alpha, there's no coefficient of z to the minus 1 because everything here, all the terms in this series alpha have powers greater than 0, greater than or equal to 0. And if I look at this right-hand term, well, to get a minus 1 in the exponent, I would have had to have r plus in being 0. And then when I've taken this derivative, it's vanished. So there can't be a 0 coefficient. It can't be a coefficient of, there can't be a residue in this series expression. So I have my contradiction. So this argument works for Poizat's example, but it also works in any type of example in this family. So I quite like this proof. So in our paper, we go on to try and understand what we can say about the algebraic relations between solutions to a single one of these equations or between these equations. And again, because of trivia, sorry, let me do this other example first. So this is sort of a strange example. So a family of differential equations that arise that's somewhat related to the Poizat examples are these Lienard equations that arise in oscillating circuits and have applications in a number of places in physics and engineering. So these are second order equations where f and g are rational functions. So what I want to do is look at an equation. So I want to be in the sort of setting we were in the last theorem. So I want f to have no antiderivative. But now I just want to take some algebraic, some generic g. So I'm going to, but generic over the constant. So I take a rational function where the numerator has degree n, the denominator has degree d, and these are all algebraically independent. Then the theorem is the generic type here is orthogonal to the constants. And this tells you things like, well, you can't get Liouvillean generalized solutions. Okay, so the setting is I have some equation like this where I have generic constant coefficients. And there's a theorem of Jaoui, a fairly interesting theorem. It's a specialization theorem that says that in certain families, you have a family of definable sets, and the generic fiber, the generic type of the generic fiber is non-orthogonal to the constants, then all the fibrils are orthogonal to C. So in this case, if I just think of this as a family where I let Ci and Di be any constants, if I let the C's be 0 and the D's be 1, I get back to this sort of generalized Poizat equation that we know is orthogonal with the constants. So that tells me that the generic fiber has to be orthogonal to the constants as well. Okay. I still find this to be a bit of magic, but it's a nice result. As I said, we then go on to try and understand algebraic relations between solutions. So again, we only have to look at things two at a time because of triviality. So suppose I have two rational functions with no antiderivatives, and I allow the possibility that they're the same here. And I want to look at a generic solution to F and a generic solution to G that are generic over K. And I want to know, and suppose that they're interalgebraic, model theoretically interalgebraic, which would mean that over K, the algebraic closure of X and X prime is the algebraic closure of Y and Y prime over K. Then what we prove is that in fact, in this case, the algebraic closure of X and the algebraic closure of Y over the constants are already the same. I'm not going to say much about so in particular, if Y is in the model theoretic closure of X, then it's actually in the algebraic closure of X over the constants. And we use a little bit about trivial strongly minimal sets here, but mostly it's a fairly algebraic argument about Kähler differentials and transcendence that builds on the work of Ax in his proof of Shanuel's conjecture for power series, Rosenlich, and later generalizations by Bristovsky. If you find this stuff interesting, I encourage you to look at our paper. Okay, so that says that if I'm trying to understand algebricity between solutions, I really only have to look at if I want to understand model theoretic algebricity between solutions, I only have to look at algebricity over C between solutions. So if I have two solutions like this and they're interalgebraic, then in fact there's some kind of algebraic function such that phi of x equals y. I'm thinking of the complex numbers. This can be made precise anyways, but this gives you the intuition here. So I've got some algebraic function of x, some solution to some polynomial over x that gives me y. Okay, so let's differentiate. Y prime is phi prime of x plus times x prime, and differentiate again. Okay, now I have this expression y double prime is g of y prime, and I have expressions for y double prime and x prime, so I can get rid of those. So I get that y prime g of y is phi double prime x prime squared plus phi prime x double prime f of x. And now I want to use the fact that y is phi of x. So I get rid of the y on the left-hand side. And now I'm so just solving this for phi double prime, just rearranging the terms, I get that phi double prime of x is times x prime is phi prime of x times g of phi of x minus f of x. Now this is so phi double prime of x and phi prime of x are just algebraic things. So this is a first order differential equation involving x. And there aren't any of those because x is the generic solution of a second order differential equation. So this can't happen unless phi double prime is 0. Okay. Well, what does it mean for phi double prime to be 0? That means phi of x is just an affine transformation, ax plus b. But not only that, if phi double prime is 0, that means this side is 0. Okay, phi prime of x is not 0. Since it's a. So in fact, what we have to have is that the only way this can happen, the only way I can get this algebricity between solutions is there has to be a linear change of variables, so an affine transformation phi, such that f is g composed with phi. So let's state that as a theorem or a lemma. So first of all, let's look at the case where f and g are different. If they're non-orthogonal, if these two strongly minimal sets are non-orthogonal, then it's because g is just an affine change of variables from f. So we can obviously get those and get examples of non-orthogonality, but that we can also tell when two things are orthogonal. The other interesting thing what happens is what happens when F is G. Well, that says that two solutions can be algebraic. Then there has to be some phi as above, such that F is phi composed with F, and that f of x equals y. Now, for most F, that doesn't happen. This only happens if phi is the identity. So for most rational functions F, this says that the closure of X is singleton X. But that's not always the case. Here are two examples. If f of x is 1 over x minus a minus 1 over x minus b, then the rational function a plus b minus x fixes f. And if f of x is 1 over x to the n minus 1 and phi is just multiplying by a primitive nth root of unity, that's an example. So these are going to be examples where on the strongly minimal set, I have a non-algebraic, a non-trivial algebraic closure relation. Sorry, I have a the algebraic closure relation isn't just the identity. But let's look at this a little bit more. Suppose F has finally many non-zero residues. And if F is F composed with phi, then phi has to permute the residues. But I know that the group of affine transformations is sharply too transitive on C. So there are at most n times n minus 1. Once I tell you where alpha 1 goes and where alpha 2 goes, I know the whole permutation. So there are at most n times n minus 1 such phi permuting these things. So that would tell me that the closure of X, in any of these, in this example, the closure of X at most n times n minus 1. So in particular, it's Aleph 0 categorical. I have to do a slightly different argument if there's only one residue, but this is fine. So this tells me that in this family, all of the strongly minimal examples are Aleph 0 categorical. And in fact, you can sharpen this result from n times n minus 1 to n. So and show that in some sense, the two examples I gave you before are almost the only examples here. Okay, I have a couple minutes left, so let me say a little bit about the non-strongly minimal case. So in this case, my function f has an antiderivative. So, so I have this family of rank 1 subsets, so that this thing has rank 2. But sort of almost anything could happen after that does. So there are three possibilities. First, I could be in a simple case where my rational function is just a. In that case, I have a linear differential equation, so it's actually internal to the constants. In that case, VF is just, it's a two-dimensional vector space over the constants. A second example, a type of phase example is, it's possible that all of these fibers are also non-orthogonal to the constants, but not in a uniform way. An example of this comes up if I take f of z to be any linear term. Then these end up being, all of the fibers end up being non-orthogonal to the constants, but not uniformly, so it's not internal to the constants. But so you have a two-step analysis that's not analysis. And the third possibility is that the fibers are themselves non-orthogonal to the constants, and this happens also. This happens in the case where my rational function is, say, a generic polynomial. And my guess is that this happens in almost any other case except for the two things we set up here. So in the non-strongly minimal case, you get some interesting phenomena as well, more or less anything you might expect might want to happen. Okay, so that's it. So I want to thank you again for the invitation to speak here, and please join me once more time in wishing happy birthday to Kobe and Sergey.